Welcome back, guys, and today we're here for another video. And so today we'll be discussing Hardy-Weinberg and the equations exactly. So, for today, since I like focusing on the math aspect, I'm just going to be focusing on the math part essentially of what makes, Hardy-Weinberg interesting to me and, why it works and how you be able to solve, problems like that as well. But before we get into Hardy-Weinberg, we must realize that there are five different aspects that contribute to why Hardy-Weinberg equation is real in the first place. And so essentially it is just a way of saying that there's no evolution, and this is, a fairly, very, very almost correct estimation of what would happen to a population size if it never evolved, if it never mutated, if it never had anything to make them different. And so first off, we have random mating. Obviously, if you have, you know, if you're making certain, animals or species mate, and you're saying that this is, natural, it is not natural because you are artificially mating them, and therefore, if you were to let them go, then that would be Hardy-Weinberg. And so number two would be no gene flow. This means that there's no in and out, there's no migration, there's no species mating with other species, there's nothing contributing to, changing the population size or changing, uniqueness in the species. Number three, have no mutations. Obviously, that means that let's say you had a chicken, yellow chicken mates with a yellow chicken, and one of the mutations will be a black fur chicken. That would not happen in a Hardy Weinberg. That just wouldn't happen. Number four, we have a large size. If you have a small size, my interpretation of this is that it goes like the castle effect of I'm sorry, founder's effect, where you know, it's kind of like a bottleneck. You have a small size, so therefore it just turns all bland, and you don't really get anything different. But you also don't get that estimation if there was like, a large size compared to, just a small size like the founder's effect. And number five, we have equal fitness, aka that fitness that every single type has the same probability of living and surviving and being able to reproduce, because essentially fitness is not just being able to survive, but it's also being able to reproduce. That is what fitness means. And so these are the five, categories, rules, expectations. These are just the five main things that you have to do before you're like, oh, this is Hardy Weinberg, and then you start setting up the equations. And so it's time to get into the math part because I really don't like the sciencey part. When I took AP Bio, this is confusing, and I just like the math part. So we have two equations. We have P plus Q is equal to 1, and then we have P squared plus 2PQ plus Q squared equals 1. And I know this is very confusing if you barely just started doing Hardy Weinberg, or you just barely started getting into it. But what essentially P just means the dominant allele. And so this is the allele that isn't most present because that's something else. But it's just the dominant allele. So obviously an allele could be like AA, big A, little a, then AA. The dominant allele would just be the uppercase letter. And so essentially what that means is if you have a gene and that gene has a dominant allele in it, that dominant allele masks the recessive allele because you only need one dominant allele in order to show that, that phenotype. So we have P, which is the dominant allele, and we have Q, which is the recessive allele. And so essentially, you might figure out why they're supposed to be equal to 1 because it's constant. There's nothing changing, so therefore both equations kind of have to like piggyback each other. And so it'll make more sense once I got one. But essentially, you're saying that the dominant allele plus the recessive allele will equal to a constant, which will never change, which is why we choose 1 for in this instance. And honestly, it gets kind of confusing, but here's my interpretation of it. So you can see how you have p plus q is equal to 1, right? But you might be like, well, why is p squared plus 2pq plus q squared equal to 1? Well, my interpretation of this is that you can actually factor the um the equation. So essentially, you can factor it to just have p plus q squared is equal to 1. Because if you remember from algebra 1, algebra 2, whenever you took algebra, you could just do the square double square, or you can just FOIL. From here, you get p squared because two p's. Then you get qp, which is just plus 2qp plus q squared. And so that's my interpretation of it. That's where you get it from. And here's another way to figure it out. So if you remember from your Punnett square, yes, the Punnett square, if you were to do PQ mixed in with PQ, you get P squared, PQ, PQ, and Q squared. And so essentially, well, I didn't explain it. So essentially, what this means that is for the first equation, so we're just going to call P plus Q the first equation. We're saying that the dominant allele plus the recessive allele is equal to 1, therefore it's constant. And then the second equation, this one, P squared plus 2pq plus Q squared, that is the phenotype. And you have to remember this very, very carefully because in the square below, we see that the dominant allele is in 3 of the 4 boxes. So this means that 75% of the phenotype will be the dominant allele, or will be the dominant allele showing. What this means is that the two equations might look similar or might look the same, but there's a huge difference when you're calculating it. And so when I solve problems, you see what I mean. But essentially, if you have P in 3 of the 4 boxes, that means 3 out of 4 times that species that reproduces will have the dominant allele with the baby, or with whatever species, or with whatever whatever they reproduce with. And so here's what I mean. So let's say you have 100 cows, right? Simple enough. 36 of them are white, and then 64 of them are black. And now let's make white the dominant allele, and let's make black the recessive allele. So essentially, we're gonna try to find all the p's and q's of the equation. Or if you really want to be fancy, let's just say we're gonna try to find for 2pq. We're gonna solve for 2pq. Now, the first thing you have to do whenever you do any kind of these equations is you always want to find the recessive phenotype first. And here's what I mean. Because as you know, with a dominant allele, whether the the gene is dominant, is homozygous dominant or heterozygous dominant, that dominant allele will always show, no matter what. Because as I told you before, the dominant allele will always mask the other recessive allele, and the only time a recessive allele will show on the phenotype is when there are two recessive alleles. And so that means that you can't just go for the dominant phenotype because yes, you can get the heterozygous and the homozygous, but you don't know which one is truly which because you have p squared plus 2pq, but this just shows the dominant phenotype. And so if you're really good at pattern recognition, you can see that we're going to work with decimals. So Let's say we're trying to find Q squared, right? Which is a recessive phenotype. So how do we do that? Well, we see that we have 100 cows, and we see that 64 of them are black, which is a recessive phenotype. So from here, we can just do 64 divided by 100, which is just 0.64. Now, this will be your Q squared. And you might be wondering, well, how may I find Q? Because we've already found Q squared, and we're working with decimals here in order to add up to the one. So essentially, in order to just find Q squared, just square root it. And in order to make this more simpler, instead of square rooting the actual decimal, just square root the fraction. We can see here that the square root of 64 is just 8, and then 100 is just 10. So we can see here that Q would just be equal to 8 over 10, or zero point 0.8. And this is amazing, because that means with a little equation manipulating, we can find P. So we know that P plus zero point 0.8 is equal to 1. And so what I did here was I just changed the recessive allele frequency to zero point 0.8, because that is our Q. And so from here you can just minus zero point 0.8. And so we see here that the dominant allele frequency is just equal to 0.2. And so this will be our P, because as you can see, zero point 0.8 plus zero point 0.2 is equal to 1. Now, this might seem a little bit confusing at first. We found P and Q, but what does that mean? Now we find the allele frequencies. Now we have to find the phenotype frequencies. And since we were found Q squared to be 0.64, we can just write that down somewhere. And so how exactly do we find P squared? Well, the answer is simple. You just square the P. And so from here, you do P squared is equal to 0.2 squared. Or if you want, you could just do fraction. You could just do 2 over 10 squared, which is just equal to 4 over 100, or 0.04. And now from here, since we're trying to find 2PQ, all you really have to do is just again just put your variables in. So we know it's just 2 times 0.04 times zero point 0.6. I'm sorry, it's just 0.2 times 0.8. And so really, I think you'll be given a calculator for this, so I'll just be using a calculator. You can use any calculator, because I think in the AP test or whatever they give you, I don't think they'll expect you to know how to do decimals. I hope not. And so from here, 0.2 times 0.8 is equal to 0.16 times 2 is equal to 0.32. So this means that the heterozygous frequency is 32% of the population. So this means that 32 cows will have a dominant allele and a recessive allele. But since they do have a dominant allele, this means that they'll just have the dominant phenotype. And so from here, this makes a lot of sense, because we have all our values, and you'll see why Hardy-Weinberg works. So since we know that 2PQ is equal to 0.32, since we know that Q squared is equal to 0.64, and P squared is equal to 0.04, all we have to do is just add them up and see why it works. And you should get one. Now, obviously, I didn't use a very, very large size, but this is just an example as to show you how to do the mathematics for Hardy-Weinberg and why the equation works. And just remember, if your values don't add up to 1, You did something wrong. I am sorry to tell you, but you did something wrong if your values don't add up to one, because if they did, then that means either your population is changing or you done goofed up the problem. But essentially, that's just a little Hardy Weinberg. Uh, I'm not really an AP Bio wizard like that. I didn't really like bio when I took it, honestly. I mean, I like the math portion, but I didn't really like, just like having to know everything and why there's so many exceptions and like, oh, why these two dudes were like, oh, if we have like 1,000 cows, they won't change. Like, it just doesn't, I don't know. It was just weird. But this is the math part, honestly. And it's really, really simple. As long as you practice and you get more used to it, it's just like solving the equation. You're just putting variables in, you're getting variables out. I'm sorry, you're getting variables in, you're getting variables out, numbers in. It's just manipulating the equation. And honestly, it's very, very simple. If you just practice enough, then it's very, very simple. And so that's just one problem. If I didn't explain it too well, please go in the comments and you know leave some feedback, leave some advice, see how I can explain it better if you need more help. But this is my interpretation of Hardy Weinberg. You know, thank you for watching. This is a really, really tough video for me because this is it was difficult for me, honestly. But I hope you understood. Thank you for watching. Goodbye.